of multidisciplinary research and development experience at CSIR National Physical Laboratory, New Delhi, at Indian Institute of Technology, Delhi, and AIMS, New Delhi, in the field of physico-mechanical metrology, infrared and Raman spectroscopy, and near-field microscopy. Presently, she is working as the chief scientist and head of the physico-mechanical metrology division at CSIR NPL, New Delhi. She has received various accolades, and we are fortunate to have both our chairpersons with us here today. I would like to invite our chairpersons to the stage so that they can commence the session. Cordless mic दे दीजिए. एक और.
Thank you. I thank organizers for inviting us, and it's a great endeavor, especially to arrange a conference of such kind in colleges is really a big task. And for that, I congratulate Dr. Pratibha and her team for this wonderful job. Uh, since due to paucity of time, we will not be able to extend the talks as given in the schedule, and I request distinguished speakers to restrict themselves for 20 minutes, and then maybe 5 minutes for questions, if any. And now I'll request my co-chair to introduce Professor Avasthi.
Thank you. And first of all, I would like to thank the organizing committee for giving me the opportunity to be here. And this particular session has three talks. And I request all the speakers to take only 20 minutes time because we are running late. So first speaker in this talk is Dr. Professor Satish Kumar Avasthi. It is my pleasure to introduce him. Uh, Although I think he's very famous in DU and I mean he's a very famous scientist, but still it is it is my duty to say a few words in his honor. Professor Satish Kumar Avasthi joined Department of Chemistry, University of Delhi as a reader in 2002 and currently working as a professor. He received his doctoral degree from University of Allahabad in 1991. He received DBT Research Associateship in 1993 and moved to Indian Institute of Sciences, Bangalore. He got an opportunity to work with Professor Peter E. Nelson and at Denmark and in the newly emerging and promising area antisense properties of peptide nucleic acid PNA and published several research articles. In 2001, he moved to USA and joined Department of Pharmacology, Robert Wood Johnson Medical School, New Jersey, and later he joined Institute of Massachusetts Medical School, Department of Biochemistry and Molecular Pharmacology. Dr. Avasthi is recipient of many international research fellowships, for example, Tokyo Institute of Technology, UNICEF Fellowship Award in 1997, ICMR International Fellowship for Young Biomedical Science 2008, INSA Exchange Program Visiting Scientist Award in 2010. He is life member of several scientific organizations. It is very difficult to speak all. So he has done a good amount of work, and I think he is well known to all of us. Now I request Professor Avasthi to please come and deliver his talk. Professor Avasthi, please.
Hello.
Thank you, Professor Avasthi. Professor Avasthi, I will request you to take only 20 minutes.
I'll take 15 minutes, don't worry.
Okay,
I'll finish
thank
because
you.
I'm also in a hurry.
Okay, thank you.
Okay. Thank you very much for a nice introduction. And also thanks to Dr. Pratibha for inviting me to give a talk. And it is good that they have cut down my time. So I'll cut down my 5 minutes from my side because I have to rush to university. Okay. All of them are from Delhi University except few people who are here, and they are aware of this building. This is the administrative building of Delhi University, but I am showing this building not because of the administrative building, but because of something else. You please guess it. I will show in the last. Okay. So my group is working on several aspects because I am basically chemist, but I am working on the chemistry and biology both sides. So this is interdisciplinary talk. And some of the students are working on the material aspect, because if you go around, you will talk people. Every student is running behind this material chemistry, material science, and nanoscience. But nothing is like material science, nanoscience, and material chemistry. It is only chemistry which is behind this material science or nanochemistry or nanotechnology. So some of the people have worked on this nanoscience and they have published a couple of papers. And but I'm going to talk on the synthesis of a tetraoxane against the malaria parasite. One can ask the question, why malaria parasite? Why there is no vaccine against the malaria parasite? The vaccine is even developed against the COVID virus. There must be some reason. I'll let you know in a few minutes. But yesterday I was reading some article, because yesterday I prepared this talk because I just slipped my mind. I had to go and give a talk. And then I found there are three diseases which are very common in India. One is the cancer. The numbers are increasing every day. This is as an alarming rate. And this is because of the related with the environment. This is related with the pollution. And then the other one is tuberculosis. It was mentioned by Professor B.S. Chauhan in the beginning. The highest percent of the tuberculosis are in India worldwide. Okay? And there is still no drug because of drug resistance. And we are going to talk about the malaria. Malaria is one of the oldest diseases exist on the earth, and there is no vaccine till now, though vaccines are available for other diseases. And this malaria parasite was discovered by a French doctor, the Sir Ronald Ross, in 1897, and he got Nobel Prize in 1902. And this recent world report shows that the 241 million people, 240 million cases are reported worldwide against the malaria parasite. Now this is the timeline of the cases reported worldwide, but there are 5 species which are very common against in malaria, and there is a Plasmodium falciparum, Plasmodium novelski, Plasmodium vivax, OL, and malariae. The first disease, this first species is very dangerous. It is lethal against the human. Fortunately, this strain is not available in India, and that's why we have got a low death rate against the malaria. And this the symptoms are high fever, sweating, headache, nausea, vomiting, diarrhea, anemia, and so on. And the most target are young children, pregnant women, travelers, and migrants. And who is the responsible for transmitting the malaria parasite from one place to another place? And the most notorious is female anopheles. In general, females are very safe as compared to the other species. Now, what is the impact here? You can see here there are 3 places where the malaria parasite attacks. Now, this first drug was discovered, uh, and it was discovered by Pere Joseph Peltier and Joseph Condon in 1820, and they isolated this compound from the plant, the cinchona bark, that is quinine. Though quinine is now drug resistant, but still doctor prescribed along with other combination of the malarial drugs. This is the time frame of the malaria drugs. And the first drug which was developed by the Joseph Perry, because he isolated this compound from the plant in 1820. Then this is another synthetic molecule, because this was from natural source. This is synthetic, the chloroquine. It was 1934, and then pavamethine. This is again a synthetic compound. And now this is artemisinin. This was isolated from a plant source, that is the herb, in 1972. This is a natural compound and known as a magic drug against the malaria parasite, and that is the mefloquine that was synthesized in 1974, and uh, and this is the only drug which cures all forms of malaria parasite. None of the other drugs cures all forms of the malaria parasite. And this drug, this is a basically doctor, and she was working on a plant chemistry, and you too discovered this compound that is isolated from the plant source and got Nobel Prize in 2015. This is the lady who got Nobel Prize for only discovering of single compound, no one else in the history. Now, this compound shows activity against antifungal, shows fungal, bacteria, and viral, tumor, protozoa, and helminthine, that is inflammatory. But this is the most effective against the malaria parasite. It has got several disadvantages, but these are three compounds which were chemically modified and synthesized, and they are currently used because of the bioavailability of this molecule. There is dihydroartemisinin, beta artemether, and artesunate. And these are the most potent nowadays used against the malaria parasite. Now, one can ask the question, why this malaria parasite doesn't have any vaccine? What is the reason? Recently, we have developed vaccine against COVID. We have got vaccine against tetanus, influenza, and so on. But why there is no vaccine against malaria parasite? Now you can see here the life cycle of malaria parasite is very complex, very complex. It consists of in two parts. One part is sexual, that is completed in a mosquito phase, and the other part is asexual, that is completed in a human being. Right? Now, if you find a drug which may work in the sexual phase, it may not work in the asexual phase. If you find a drug which may work in the asexual phase, it may not work sexual phase. And this is the reason till now there is no vaccine, only the drugs which are being used to treat at the blood stage of the malaria parasite. Now, this is a simple representation of how does this happen. I'm not going into detail. There are two enzymes, that is cysteine protease and plasmapsin, and these are responsible for the degradation of the blood. So the hemoglobin there, the hemoglobin, which is the picture shown the RBC, the hemoglobin, and hemoglobin is attacked by the parasite, and then it forms the heme, and then the heme is converted into hemojoin. This this system, this subject is extremely toxic to the malaria parasite, and therefore it immediately converts into hemojoin, that is non-toxic. So most of the drugs which work here, they are stopping the conversion of the heme into hemojoin formation. Now, as I told you, this is the artemisinin, the drug which cures all forms of malaria parasite. Any form of the malaria parasite is there, then it can be cured using the artemisinin. But now WHO had recommended not to use artemisinin as a monotherapy, but use in a combination therapy. And this, it means you can use artemisinin along with another existing drug, so you can delay the drug resistance against the malaria parasite. So these are the common drugs which are being used along with the artemisinin, that is lumefantrine, amodiaquine, mefloquine, and paramethrin, and sulfonazole. So these are the drugs which are always being used along with the artemisinin just to suppress the drug resistance quickly. This is another slide showing the mode of action. I'm not going to detail into this. Now, so keeping in mind, there are two ways you keep on searching a new drug, because the recent report showed that the Nature paper last year, it showed that the malaria parasite is developing the drug resistance against the artemisinin, and this report came from the Thailand side, Thailand and Cambodia border. It means sooner or later this drug may not work against the malaria parasite. So people started looking how to make a new molecule, because the drug discovery takes 10 to 15 years to bring a new molecule into the market. So people started thinking, how can you use this molecule and modify into different molecules, so it can be used against the malaria parasite. Now, if you look this structure, you will find it has got the 3 oxygen, and this linkage, that is the indo-peroxide linkage, is very important for the activity of this molecule. So people started, we should make this type of compound, and this compound is known as a trihexane, depending upon the substituent on either side of this one. And but this has a disadvantage: the multi-step synthesis, low yield and less uh, shelf life. So if shelf life is less, yield is low, and the multi-step synthesis, then in the last, the cost of the molecule, the cost of the drug will be high, and malaria is common in the poorest of the poorest countries, like South Africa. The malaria is rampant, and there is no malaria in Europe and America who can afford it a high cost drug. Then the people started thinking, how can improve this the modification in order to have a better compound. The people thought we can have a tetrahedron type of compound. The advantage of this molecule is we can synthesize in a single step, moderate to good yield, is almost same in the range, then higher shelf life and is stable at room temperature. So if you can keep at a room temperature, you can easily transport from one place to another place. You can use day, night, anytime in the hospital. So there are two groups which are very common and frequently working abroad. One is Paul Neal, and it is very big group in UK, and they have got some lead compound. They found the compound which reversed the drug resistance in the malaria parasite, and they have got some of the compounds are in clinical trial. The other group in Europe is the Jarnes Jaskara. He was the person who discovered a compound used to synthesize the tetrahedron or trihexane type of compound. So when I came back to India, I started to start our work. The region, when you are working in Europe, you will have a lot of facilities. You can buy any chemical, you can buy anything in a 24 hours. But you come to India, this is not possible. You cannot. You have to try to get fund. You have to try to get a student. You have to create the infrastructure own, because the university or other institution will provide a simply room. Then you have to manage everything. So I started to work on this type of compound because it's easy to synthesize. So I'm not going to previous result. So I'm moving on the next step. So I thought what we should do it. So there are two ways you can synthesize this type of molecule. Either you can have a symmetrical or you can have an unsymmetrical. So if you have a symmetrical molecule, it means you can have a lesser number of compound. But if you have got an unsymmetrical molecule, then you can have a diversification of the compound. You can have a large number of library, and you can screen against the potential activity against the malaria parasite. I also looked the literature. We found there are only limited number of methodology are available for the synthesis of a tetrahedron. So I'm not going to detail into each step. Then we thought what we should do it. The earlier journey which I showed you in the beginning, this group has developed one small molecule for the synthesis of tetrahedron, but the compound is very expensive. And this is the methyl rhenium oxide, and rhenium oxide was developed by Jaskara. Okay. Now you can see here the cost is very expensive. 100 milligram cost 2,596. And then if you have got this nature, is moisture sensitive and light sensitive, and catalytic efficiency is moderate efficient, it is around 20 to 75%. Yield depending on the subject used for the chemical synthesis. Then there is another compound called rhenium oxide. It is also expensive, but it's cheaper than the methyl rhenium oxide. The 2 gram costs 6,742. This is crystalline and moisture sensitive. Good efficiency with 40 to 80% yield. Now, if you want to use this expensive chemical for your synthesis, you want to synthesize 1, 2, 10, 20 compound, this is fine. But if you are working on a drug discovery, then you need to find a compound which can be used for the design and synthesis of a large number of compound in order to have a cost effective. So we are looking, because initially we synthesized molecule tetrahedron using these two catalysts, but I found these catalysts are very expensive. And when I asked the student to do the synthesis, what they do it, they do one reaction, next time they throw into sink, and the third reaction nahi hui. So we are trying to find out the alternate, how can you minimize the cost of the chemical synthesis, and we found out that the molybdenum trioxide is the best in the synthesis of a tetraoxane. It is cheap, 50 gram cost 1133 rupees. It's a no moisture sensitive, no light sensitive, good efficiency, and easy to handle. So we decided to work on the tetraoxane synthesis using this newer catalyst. We have got this patent on this molecule, and using this one, we synthesize a large number of tetraoxane, and this is a 1 mole catalyst with hydrogen peroxide and this solvent, and we got around 40% yield in 60 minutes. So rest of the synthesis which I'm going to show here are synthesized using this type of molecule. So I'm going to discuss only 1, 2, and 3 compound here. Rest I'm not going to discuss in this talk. So this you can look at here, this molecule. This is the triazine molecule, and beauty of the triazine, those who are chemists over here, they can easily catch that it contains a 3 nitrogen to ring and 3 chloro in the bonded with the benzene ring. And the beauty of this molecule is you can replace 1 chlorine atom at a time, or you can replace 2 chlorine at a time, or you can replace all 3 chlorine atom at a time, or one by one, depending upon your requirement. So we started making this type of compound, and we got this very good result with this compound. These are the hybrid compound, because earlier I showed you that WHO had recommended not to use as a monotherapy, but use as a bitherapy. Most of the nowadays the drugs doctor prescribe, they are combination form. It means they are acting on the body as in a synergistic way, that one form may work, one form may not work, or both are working in a synergistic way, but single dose may not work because of that drug resistance. So this is the combination of hybrid molecule. When you have a combination, the effect of the each drug in the body will have a different. One can be excrete through urine very fast. It can be one can be retained in the body, but when you have got hybrid molecule, the mode of action will remain in a synergistic way, but both can be retained in the body and they can release from the body at the same time. So synthesis is very simple. We reacted ketone with N-benzoyl piperidinone in presence of molybdenum trioxide, and we got tetroxane. Now, if I'll discuss the little bit characterization. The synthesis of characterization is very simple, but characterization of this molecule is very difficult. After synthesis and in vitro screening, we found the that one of the compounds showed extremely good activity with minimum toxicity. The toxicity is also very important. Suppose you find a molecule which is showing good activity, but if it is more toxic, there is no use for the human being. So we found the minimum toxicity, that is 100 macromolar. This molecule is not toxic to human cell, and this has got 6.35 nanomolar activity, while the artemisinin shows 5.97 nanomolar activity, and these are the other activity. And if you can see over here, most of the compounds are showing less than 100 nanomolar activity, but some of them are showing less than 10 nanomolar activity. Now you see here, those who are chemists, they can say, oh, this is awful spectra. Compound is not there, but we have an experience by looking the old peptide synthesis, because if you work on the peptide and if you are working on the beta sheet peptide, you will have a similar type of a structure, because beta sheet peptides aggregate, and if they aggregate, in order to have deaggregation, we need to use some polar deuterated solvent. But instead of doing that, I just move on the C13 NMR, and because there are 2 characteristic carbon over here, these are 2 quaternary carbon. So if you find these 2 quaternary carbon, you can assume that this is the correct structure of the molecule. But even I did not believe, because when you start believing your student, you are always in danger, because the era is techno, because they can 1 minute. So this is the mass spectra. Mass is showing correct, but I learned from my previous boss. If you publish paper, you can have a crystal structure, but if you get the crystal structure, no one can raise the finger. So that's why I learned from the previous class, all my paper have got one crystal structure, irrespective of the number of the compound published in the paper. So we got this crystal structure. Now this is sulfonyl type of compound, this is a acyl type of compound, and that confirms your design stage is okay. We got the correct molecule. And this is the, I'm not, 1 minute I'll take it. Now you can see here, this is 3D7 strain, and here DD2 strain. This is the chloroquine sensitive, and this is the chloroquine resistant strain. Now, I'm not going to discuss here because of shortage of time. You can look it over here. Now, this has got 253.4 nanomolar activity against the drug resistant parasite, but most of our compounds are in the range of 100, less than 100, except the first one and second one, last one. So this design criteria works very well. We have patented this molecule. We have already moved to a company, those who are working on this type of problem for other further clinical studies. So conclusion, I am skipping some of the slide. A series of different types of tetragens were synthesized using cost-effective and convenient protocols. A newer atomic catalyst, molybdenum trioxide, were used for the synthesis of all types of tetragens instead of using an expensive catalyst. The synthesized compounds were well characterized using NMR, mass, and single crystal XRD. And the synthesized compounds showed a good nanomolar range activity both in vitro and vivo. More work is going on in this direction. And the sum of the fund, I got it from the University of Delhi because that is providing a bread and butter along with the fund. Then UGC, DST, and UKRI, that is Indo UK, and I got some money from the Nano Micro Limited UK. So now last slide from this side. I showed you the first slide where the administrative block was there. Could you guess why I showed that one? सारे लोग तो यहीं दिल्ली यूनिवर्सिटी से हैं. किसी को आइडिया हुआ क्यों हमने दिखाया तो स्लाइड? Anyway, I'll show you. This building has got historical importance because where I go, I showed this slide because I have got a special affection for showing our feelings. Okay? Below this building, there is a room where Bhagat Singh, when captured during British period, was kept, and then he was transported to Lahore for execution. So this is the room where he was there. So this is the room where he was kept for, I think, 12 or 14 days, and after that he was transported to the Lahore for the execution. And this is the plate. If you get chance, because it's always open in working days, I would advise every student should go and visit how this country. When he was kept in the room, dark room, there was no light, nothing was there, no window was there. So this will always motivate how that we got this independence after sacrifice of such type of people. And this is this work which I presented were done by Preeti Singh, and currently she's working on this one. This is the malaria work. Others are working on a different aspect of the chemistry. Thank you very much.
So, our time is too short. So, one question, please. If anyone has a question, I think we can take one question. I think Professor will be available in lunch time. So, anyone can go and discuss.
Yeah,
Yeah,
sure.
please.
We have tested the derivatives of artesunate into in 3D7 and DD2 strain, which are chloroquine sensitive and resistant. Have you tried for the artesunate resistant strains also? Whether these
No.
derivatives
No,
have worked
no.
there?
No. Thank you.
So, let's thanks Professor for giving such a wonderful talk. Thank you.
We would like to felicitate Avasti sir, and we would like to thank him for enriching all of us with such a brilliant talk. I request the chairpersons to kindly felicitate him. We would also like to gift him a painting made by our industrial chemistry student Chanchal. There's a painting which Chanchal has made, and we would like to gift it to sir. Chanchal, you can please come on the stage. Thank you so much.
Okay. Thank you, Professor Avasti, for the nice talk. And now I would like to invite Dr. SSB Ramashastri.
Yes, yes. I'm here.
Yeah, oh, is there?
Okay.
Just a brief introduction of the speaker. Professor Ramashastri did his PhD from ISC Bangalore, and then his postdoc from Scripps Research San Diego, and then he joined ICHE Mohali. Now he's associate professor there. His research interests include development of sustainable and atom economic reactions by organophosphine catalysis, palladium catalyzed allylic alkylation reaction, one-pot cascade transformations for biotic natural products and pharmaceutically important compounds. He has been recipient of CDRI Award of Excellence for Research in 2022, and then very prestigious DST Swart Jayanti Fellowship from Government of India DST, and then AVRA Research Young Research Award in 2018, then TM Chemical Journal Award, and he was admitted to MRSC, which is member of Royal Society of Chemistry, in 2016. He is also fellow of FRSC, and he's there in advisory board of many reputed journals like organic biomolecular chemistry and other RSC journals. So I would request you to speak for 20 minutes.
Sure. Thank you. Sure, ma'am. Definitely.
Thank you.
Thank you very much. Thank you very much for the kind introduction. As the chair mentioned, I'll be as brief as possible. Before that, let me thank Dr. Pratibha for her wonderful efforts organizing this. I'm really happy to be here. My first time at this college, as such, affiliated to Delhi University. As the chair introduced, we pursue different fields of chemistry, as you see here. Transition metal catalysis, organocatalysis, that is employing phosphines as catalysts. And we have been recently into sulfur-related chemistry. Our intention always is otherwise applying the methods that we develop to synthesizing bioactive natural products. So what I'll do in this talk is, due to the paucity of time, I'll stick to the chemistry that we have contributed as of metal catalyzed transformations. I'll also show you how we applied our chemistry to synthesizing some relevant natural products. So there are several carbon-carbon heteroatom bond forming reactions that we know of. This has been the textbook chemistry, and some of this chemistry has been awarded Nobel Prize also. Some of them, as we all know, Heck chemistry, Suzuki, Negishi, and others. Among all of them, this particular reaction, that's the Suzuki-Trost reaction, which is otherwise called allylic alkylation chemistry, attracted our attention. Very briefly, to introduce what is this chemistry, it involves the reaction of allylic substrates having a leaving group upon treatment with palladium 0 forms these parallel palladiums, which can be trapped with appropriate nucleophiles, and that can lead to the formation of these two types of products. This is quite well established. Even inertial selective transformations are quite well established, and the applications in natural product synthesis is also very well aware of. What is less known as of this chemistry is the chemistry pertaining to the dianylic substrate. If you see the difference between this substrate this has allylic, this is dianylic. Once you start employing this chemistry and dianylic substrate in presence of palladium, it forms vinyl parallel palladiums, which can be now trapped by nucleophile. Against two products in this case, you get in principle 3 products, depending on the nature of the nucleophile and also the kind of substrate that you are employing or the reaction conditions. So if you see carefully this intermediate, the electrophilic component, that is the parallel palladium, which is electrophilic in nature, is one end, and we saw that there is a sort of electron rich component on the other side. Electron rich, it can be depending on the R group that is connected to the pi system that you have on the other end. So our intention was, if we can bring together these two ends, that is this electrophilic end and this nucleophilic end together, somehow we can possibly accomplish a carbon-carbon bond forming reaction that can also lead to the formation of a 5-membered ring potentially. That was the idea. But this is something that was not known till we actually conceived this plan. That means we need to do something in addition to what it is as of the substrate design is concerned. To that extent, what we went on doing was to introduce these R2, R3 groups in a dianylic system. What we envisioned was that these two components can potentially induce what is so-called axial A13 strain. Thereby, the geometry of the molecule can be reorganized in such a way that the two ends can meet together in such a fashion that is mentioned here. Now this can be in a situation to undergo what is so-called intramolecular aldering type cyclization that can form this allylic cation, which eventually upon proton elimination can form either this cyclopentadiene or this cyclopentadiene. That was the simple idea. So if you see, this model is similar to a stick model. That is, if you have a stick and if you try to bend it by force, for example, these two ends come together, right? It's analogous to that. That's what we wanted to employ so that these two ends come together. So accordingly, when we introduced actually the two methyl groups in place of this R2, R3, as you see here, our hypothesis indeed worked. You can see here that the dianylic substrate with two alkyl groups at this position under this optimized condition. In the interest of time, I am skipping all the optimization that is involved in actually achieving this product. Form an unexpected isomer over these two that were actually hypothesized. So this product can be readily identified from this bunch just based on NMR that this has an additional CH2 unlike these two components. Otherwise, this provides access to tetra-substituted cyclopentadienes. As you people know, they can be wonderful substrates in Diels-Alder chemistry, otherwise in metallocene chemistry. We didn't stop here. What we have done in an effort to extend the scope of this method, we introduced fusion into one of the double bonds. As you see here, the same dianylic acetate, we introduced arenes and heteroarenes at this position, for example, and we expected that the respective cyclopentadiene fused arenes, heteroarenes can be accessed. Accordingly, we can actually access variety of indienes or heteroarene fused cyclopentenes as expected in very good efficiency, as you see. We also applied this method, as I mentioned in the beginning. Our intention always is to find application of what we have done in the direction we identified these natural products suitable as of this particular method is concerned. These are the natural products belonging to what is so-called resveratrol family. These are only partial list of natural. There are several natural products belonging to this family. What we did to achieve this synthesis, for example, passive roller F is something that I am describing now. The respective bis-benzylic acetate we prepared and we subjected that to the optimized condition that we developed, and we accessed this indene which was hydrogenated. The double bond was hydrogenated followed by selenium oxidation against that expectation, leading to the carbonyl, that is benzylic oxidation. It actually underwent ore oxidation, forming this indenone. Otherwise, this established a formal synthesis of passive floral F, a bioactive resveratrol family natural product. So what you have seen in quick is an isonazarov type cyclization, that is the dianylic acetate underwent isonazarov type cyclization in overall forming the cyclopentadienes. With this experience, we thought, can we maneuver the design in such a fashion to induce an Nazarov type cyclization? So it only requires a small modification of the substrate that you have utilized here, that is in this form. For example, now this design can facilitate what is so-called a Nazarov type transformation. But against this design, which is flat structure that you got here, this design actually gives us an opportunity to introduce a stereogenic center. For example, If at all you can modify or modify this R1, R2, if at all these two are acyclic substrates, you can now translate that to a quaternary carbon. If at all this is a cyclic structure, that can be a spiro center, right? Just wanted to highlight how our work is different from what was known, especially with palladium promoted transformations. That is, if you see what was known with the palladium catalyzed Nazarov type cyclizations already known, but if you see the substrate design, this is a dienone, which is a typical substrate of a Nazarov cyclization. You can also see this is a dienone, but our projected substrate is a dienylic acetate. So this is what we wanted to establish. This also can lead to what is so-called acid-free Nazarov type cyclization using non-dienones such as this. Okay, and it can also give you a cyclopentene fused arenes, heteroarenes. With this idea, after an extensive optimization, we realized that this particular design, as you see, appended to the oxindole, gives, as per our expectation, the pyroxindoles, and you can see wide substrate scope in these cases. You can see that not just heteroarenes such as benzothiophene or indoles react, and also that you would have noticed that it reacts from C3 or even C2 bonded products also you can actually achieve. It all depends on how you modify or how you prepare your starting structures and subject to these simple straightforward conditions. Of course, this can also be extended to synthesizing spiroindole oxindoles, as you see here. And what is interesting as of this particular work that we noticed while we were evaluating the substrate scope is that as long as this R1 is substituted, this reaction works as expected. But once this R1 is H, I mean to say this, if at all is unsubstituted position, this reaction doesn't provide the required product, as you see here. It only gives you deacetyloxylated product such as what you see here. Okay, nevertheless, moving further, we also extended the scope of this work to creating a quaternary carbon, as I introduced during the hypothesis explanation. You can see that variety of indines can be created, interesting structures incorporated with the quaternary carbon, you can see all the way. And you can also extend the scope to fused benzothiophene with a quaternary carbon, as you see here, and also to cyclopentene fused indoles with a quaternary carbon. These are all natural product like structures which have direct implications in synthesis. Here also we observed that without a substitution at this position, that is this position, the reaction provided a complex mixture. This highlights the role of the substituent in a successful transformation. I am going to explain this very soon when I am going to touch upon the mechanism of this transformation. Otherwise, this is how the mechanism is believed to progress. The PD0 forms this parallel palladium complex. Now this R1, that is the substituent at this position, reorganizes the substrate in such a fashion that these two ends come together in this fashion. Now this is poised to undergo intermolecular ene-type cyclization, leading to the formation of this kind of parallel palladium system, and which upon regeneration of palladium followed by rearomatization forms these products. Okay, and you may be wondering that why it is ene-type. It may be CH activation, which is something that is prevalent in chemistry, that was conveniently ruled out based on the kinetic isotope effect that we performed, which gave about 0.5 that actually conveniently rules out the CH activation pathway. We also extended the application of this work in synthesizing the natural product. For example, these are all the natural products that are under the purview of our method. Among them, we have chosen to synthesize dicroanone and thionequinone. For that purpose, we prepared the relevant dienylic acetate, otherwise allyl benzyl acetate, subjected to the optimized conditions that I've just described, which gave this tricyclic structure that was hydrogenated and subsequently subjected to CAN-mediated conditions, gave this quinone, and deprotection of this methyl group here using KOH gave access to the other natural product. Both are bioactive molecules. That is what is the dicroanone. Okay, we also extended this concept to creating a tertiary center. What we have seen so far is the synthesis of spiro and quaternary centers. This work describes the creation of a tertiary center, that is a monosubstitute. Of course, if you substitute this position with one substituent, You get, of course, a tertiary center here. This is the scope of the work. I'll be quick through this, but I'll highlight especially the important aspects of this particular work in creating complexity. If you see here, the tetracycles can be conveniently prepared in just simple reaction conditions, provided you make the required starting compounds, and making these compounds also is relatively straightforward. It hardly requires 2 to 3 steps overall. Otherwise, these are part structures of some of these natural products and also bioactive molecules such as this BMS compound. You can also see that this was extended to a compound such as indinofused indole, which is relevant in medicinal chemistry and material science. We also extended this work to one part double annihilation, just not one side. We actually accomplished this in a one part double annihilation, leading to what is so called indocines, which are well known molecules in material science, and they are also known to possess interesting photophysical properties. We didn't stop there. We also extended the work to natural product synthesis. If you see here, this is a family of diazerones, and this, if you see, 3 stereogenic center give access to different types of possibilities, and the scientists earlier have categorized them depending on the relative stereochemistry as alpha, beta, gamma, delta. As you see, if you see here, this is syn anti, this is syn syn, this is anti anti, and this is anti syn. So depending on that, the different types of notation was given to these natural products, and this we targeted especially, and we applied our method in synthesizing the beta diasterone. How we did that? We made this required pivolate, because acetate making was difficult for us, but pivolate was conveniently prepared using standard synthetic chemistry transformation. In the interest of time, I'm skipping all the details, but otherwise, this one, when subjected to optimized conditions, formed this indene, and that was subjected to hydrogenation, selenium oxidation, gave access to this indinone. And this one, when added to ethyl grignard, forms the tertiary alcohol, right? That was smoothly dehydrated using Burgess reagent, and that was globally hydrogenated under standard hydrogenation conditions. And we also obtained the crystal structure of beta diacerone, which is this particular compound. Now, what I have shown is the chemistry of monoacetates. We also thought what can happen with diacetates. Okay, if you see literature with the allylic diacetates under palladium, they were proven to exhibit 1,1 dicationic character or 1,3 dicationic character, which was trapped by bis nucleophilic systems to form structures such as this, or somewhat this one. This was the contribution of Tross. Based on this, what we thought, can we do a cascade annihilative transformation? This was the question we asked. For that, what we thought was the same 1,3 dicationic synthon, which was proven by Tross. We wanted to use now 1,3 dianionic system, so that this will formally undergo a 3+3 cycloaddition and can give you chromines. Chromines, all of you know that they are highly relevant molecules, not just in medicinal chemistry, even in material science. With this hypothesis, we actually went ahead and prepared the allylic diacetates, various types of allylic diacetates, as you see, and treated with naphthals and phenols. We obtained respective products, as you see here, and these are some of the molecules here that we made are photosensitive, and something that are unprecedented in the literature. I'll show you shortly that we even demonstrated the application of some of these molecules in photophysical studies as well. What we made an observation during the study was that not all phenols work, but only meta-substituted phenols work to give you these products. You see, these 3 products are meta-substituted phenols. No other phenols work under this condition, otherwise naphthals work. I'll show you what is the effect of meta-substitution during my explanation of the mechanism. You see here, what happens initially is that this diacetate forms this initial parallel palladium, which get trapped by these naphthals or meta-substituted phenols. What we believe is that this meta-substitution is something responsible for the reorganization of this kind of a form to something of this kind. You can see that these 2 conformers have a potential steric mismatch compared to this particular intermediate, which is now poised to undergo a cyclization, and that what leads to this particular stage that undergoes eventually reductive elimination followed by regeneration of palladium to give these structures. Of course, I can talk about all these aspects, but possibly I'll skip. Otherwise, I can talk to you in detail during lunch hours or so. But otherwise, there's some interesting aspects as you see here, that the first sea attack occurs or the oxygen attack. This is inconsistent with the literature. But I'll skip this portion. But I'll show you where we applied. Again, I told you in the beginning that we try to demonstrate the application of our methods in natural product synthesis. You see here that we made, using this protocol, we made this hydroxy carbazole and treated with this diacetate, got this particular intermediate which was elaborated to these natural products grenambine, methionine and miramycin, and it also establishes the formal synthesis of these natural products. In addition to that, we also showed the application of our work in synthesizing this bohinol D. For that, as you see here, we prepared this meta-substituted phenol and treated with this diacetate and obtained this straight away, this natural product. The overall yield of this process is almost 70% compared to the literature process, which is around 30% overall yield. Otherwise, these are photophysical studies that we performed. You can see that upon exposure of this particular molecule to 365 nanometer, which was optimized, forms this ring open structure, and that again undergoes fusion back to this molecule upon exposure to light or heat. You can see the translates. You can see that this colorless moiety, a colorless solution, going to this dark brown solution, which is this forms, and again it goes back to the original form, exemplifying the reversibility of these molecules in ring opening and reformation of the structures. This not just in solution form, we also showed in solid form. We also impregnated these molecules onto the TLC plates. You can see the reversibility proven on multiple occasions. Otherwise, after showing the application of allylic diacetates, we also showed the application of benzylic diacetates. I'll be very quick with this. Just in analogy to allylic acetates, we also expected that these two types of products should form, which is in line with Tross' proposal that if at all this product forms, it validates 1,3-dicationic equivalency of benzylic diacetate, which were never dealt with, especially under palladium conditions. Okay, and if at all product of this kind forms, it would validate 1,1-dicationic equivalency. Among all this, of course, some of the important aspects of this particular hypothesis highlighted, but I'll skip in the interest of time. But I'm just straight away showing the application of this. Even benzylic diacetate, you can see with the naphthols, give access to this dibenzoxanthines, and then this is C1 appended diacetate. Even C2 appended diacetate also work to give you respective products in this fashion. And then you can see that this just not works with naphthalene backbone, it also works with heteroarene backbone, giving access to the respective structure. These are all, let me tell you, unprecedented in the literature, this kind of scaffolds. This can be conveniently obtained using our protocol. This is yet another application of our work. I'll summarize here. Our contributions in this field, especially palladium catalyzed transformations, were invited through various publishing houses. As you see, these are some of our accounts or reviews that we contributed upon invitation in different journals. As I mentioned in the beginning, we just not confine ourselves to palladium chemistry, we also work in phosphine chemistry. These are some of our contributions summarized. We developed phosphine promoted MBH, Morita-Belli-Silman chemistry, reductive aldol, hydroalkylation, hydroacylation chemistry, vinylogous aldol. This is not yet a complete picture, but we have some other contributions, especially in sulfur-related chemistry. These are some new chemistry that we developed. Maybe in another occasion I'll talk about it. Otherwise, let me thank the contributors. Siddheshwar initiated this field, and whatever the work I showed is that of Bharat Singh and Prashant. And Prashant, he is here. He's moving to Canada for postdoc. Otherwise, Bharat Singh already moved to Canada for postdoc. With this, let me thank the funding agencies because of whom the research was possible. I again thank all of you and Dr. Pratibha and all the coordinators for this, and also the chairs for giving me this time. Thank you very much.
Thank you, Dr. Ramashastri. Very fine chemistry and very nice presentation.
Thank you, sir.
I think there should be questions from students. I'll request organizers to give them chocolates if they ask questions as incentive. Come on.
It's also lunchtime for them as well.
It's fine. Yeah, yeah, please.
Oh no, it doesn't. It doesn't give that product. If you have hydrogens, it doesn't give. It's pretty well known in the literature. Any substitution, any substitution. You need both substituted. To that extent, not one substitution. Both are required. Exactly. As I mentioned, it's a 1,3 axial strain that makes the molecule reorganize itself and get the product. Okay. Sure. So sometimes the substitutions, I showed you all the way from my first study to the last, the role of substituents. These are quite sensitive to substituents. Thank you, ma'am.
Yeah, please.
So did you try to trap the intermediate because it is intermolecule in the control experiment?
Yeah, no, not just control experiment. We want to actually develop that as a new study to trap that intermediate, but several of our efforts didn't work. Actually, you're right. That's a good idea. In fact, we thought of doing it. If you remember, there's proposal involves the formation of a cation. Want to trap it so that you can create new structures. It didn't work somehow. That tells that the cyclization is more preferred entropically compared to the trapping followed by the respective product.
Okay,
Thank you, Professor Ramashastri. We'd like to felicitate Sir. I would request the chairperson, Professor Kukreti, and ma'am to kindly felicitate the speaker.
Thank you. Thank you, sir. Nice talk. Thank you very much. Thank you, ma'am. Thank you.
We'd also like to present him the conference kit.
Oh, thank you.
And there's a special painting made by Chanchal from the Department of Industrial Chemistry. We'd like to give the...
Thank you, Chanchal. Yeah. Oh, okay.
Now take the photograph.
Thank you. Thank you, Shan. Thank you, ma'am. Thank you, sir. LH.
Okay. So, Professor Chauhan is going to be the last speaker of this session. Now, I take this my privilege to present you to Professor Chauhan. Professor SMS Chauhan has been my senior in the department, and I think just 2 years back he got retired. He has been a wonderful teacher, a wonderful chemist, very fine chemistry he has done in so many years. He has got 40 years of training and research experience in chemistry, and has been a very renowned teacher in the department. And he has got many awards. I need not to elaborate on that due to paucity of time. But he did his postdoc from Alberta, Canada, and then he was also at IIT Kanpur for some time. And he has spent enormous time in chemistry department of Delhi University and has contributed a lot. And one thing important to mention is that the organizer of this conference, Dr. Pratibha, has been Professor Chauhan's student. And many of his students are now teaching in various DU colleges. So that is again a great privilege. So, Professor Chauhan, I invite you to the stage.
ये ओपन भी तो करना है अच्छा।
Thank you, Dr. Kukreti and his co-chair person for giving a brief introduction about me. That is, a paucity of time is there. Plus, I have to also thank Dr. Pratibha for giving me this opportunity to stand on this chair to speak something, because I phoned few days back from USA that I am coming to India. Then she said, why don't you speak something in my conference? So I thought I should speak something. And these particular things, after, although I am retired completely, but when I say something to retired, nobody give any respect. Even they think that I am going to waste their time. So I thought that I should start something new, and I should not write retired. Even I am willing to work as a postdoctoral if I find a suitable teacher where I can fulfill my desire. These particular things I have, during this retired period, I got two things. I have to eat one drug because my daughter applied for visa in USA. So just like other speaker already said, that almost 90% Indian, they got tuberculosis. Although I have gone Canada and other places, but they have not find anything when I'm going there. But this time they have got a new method of detecting the tuberculosis there. So I got a latent TB. For that one, I was taking a medicine for 4 months regularly, 300 mg, and I lost near about 20 kg, 15 kg of weight. So I thought I should understand why that weight loss is there, and what is the mechanism of this particular compound is there, and why the TB is more prevalent in India. This question bothered me. So I thought, let us learn something about this particular compound, this disease, and this so on. So after seeing so many things, because I was working on so many cofactors and coenzyme during my whole 40 years. So I thought I found these two, F0 and F420 cofactor. Um, so I thought, let us correlate this F0 and F420 to our study for future. I'm trying to write a review also. So this is the part of that things is there. So let us show the first slide. I have to do here. Uh, okay. This is, I think, very riboflavin is there, and corresponding to cofactors are other things is there. Riboflavin, every day we early in the morning, unless we take some quantity, we are not going to start work in lunch or something. So every day either you are going to take egg, nuts, whatever things you are going to stay. And structure is like that one. Next one is this one is there. So other slide you have seen that at number 5 there is a nitrogen is there in riboflavin, alflavin, that thing is there. So we wanted to replace this position number 5 to with carbon. That was the one intention was there. Second was second was that see the chemistry behind that one. If your nitrogen is there, that flavine is going to have one electron and two electron transfer at one time or two times. But if carbon is there, then it is only two electrons is there, that thing. So that one we started this. This is the F0 is there. That is the where only the cofactor is there, and then the other one is there F420. Their whole molecule is there, means the flavine part plus phosphate group is also there, plus one organic acid there, and then amino acid is there, depending upon the type of isolation, depending upon the species, depending upon the um, insect or other things. So F0, this is the, if you compare with this flavine, this is flavine is there, this one, FAD is there, this is oxidized form is there, this is reduced form is there. So this nitrogen, it is responsible for one electron or two electron transfer. If you are going to change with that one, then this is a D-EJA, 5D-EJA, flavine is there, and we are going to get F420. And this one is, if it is the reduced form is there, we are going to get these two things. Very similar to this nitrogen is there. So this particular compound, it is only do the hydride transfer, okay? Whereas this one, it is one electron and two electron as the reduction is going to take place. This is the oxidation, standard redox potential is there. You see here, F420, it is having 340, and NADP, and this thing is 320 is there, whereas FAD, which is having the same type of tricyclic structure, but it is having only redox potential is 220. FMN, it is going to have, so its reaction also, it is going to be different. This one is going to have hydride transfer. So very similar, its reaction is very similar to that one. It is not, its reaction is not similar to FMN and so on. So this is, you can say that although it is tricyclic structure is there, but it is having the reaction very similar to NADP, means hydride transfer is there. You can see here that one. This one you can see that F420 things, central ring, you can see the structure very similar to NADP. H is there, and this one is like that one is there. Everything is there. So reaction, its reaction, hydride transfer reaction is very similar to NADPH, which is hydride transfer agent is there. All the biological activity and other things is going to take place very similar to that one, but its stereochemistry is going to have a different reaction. That were the things. You can see now if you are going to hydrolyze that one, F420 acid hydrolysis, then you can have F0, this one of the product is there. if you are going to see the biosynthesis of that one, it is going to start from GPT and other things, this. And here, this particular reaction, this product, you can see the mechanism like this way. This adenosine, it is going to give this particular yes, sham is there. And this one, it is going to give this radical. This is going to give that one. And so you can going to have this one. And this mechanism, now you can see that one. This is the actual mechanism is going to be there. You can see this radical, the two part of that thing is there. And this particular radical is going to generate it from that one. And you can see that it is 5-hydroxy portion is red and it is coming from there. And you can see this oxidation is there and you can get this particular compound biosynthesized. If you do the synthesis of that one, total synthesis of this one, it is going to be very difficulties there. This you have to prepare first that one. Although you can do synthesis and you can get that one. And this one is the cofactor synthesis we have collected. And you can get this particular compound. Now, we are going to talk about little bit photolyase. One enzyme is there. Photolyase, it is present in insect as well as other things. And there are other cofactors. This 5 cofactor is there. This FAD, F0, MHT, and DDT. These are there. So it is the 5 cofactor. It is present in the cryptochrome or photolyase. This photolite or light sensitive dependent repair enzyme is there, in which you can do the damage from the enzyme, damage from the UVA radiation or the sunlight in the beginning of life. When life originated, in that time there is a problem is going to be DNA is going to be spoiled. So at that time, this particular light-dependent DNA repair mechanism was there, so that you can have that dimer. It is going to convert into monomer. Here you can see, this is the UV light is there, 300 to 400. It is going to form this particular compound, this thymine or nucleic acid bases. It is going to form this kind of compound. And when there is a repair is there, then this one is going to convert into, here radical mechanism is involved, and it is again, it is going to be repaired by that one. So it is very primitive and very important reaction is there. Otherwise, life on this planet is going to be very, very difficult due to this photolyase, which repair the DNA, and our life is easier to go ahead. This F0 synthase enzyme has been identified all the organisms known to produce F420, but cyanobacteria do not produce this one. But still, F0 is present there. So it is to mimic the selective reduction of this one. So if you can get this particular compound, cryptochrome, I think we can leave that one. This is the biosynthesis of F420 is there, different species. This is Mycobacteria is there, and this one is Archaea is there, And this is another things is there. Those three is different species that biosynthesis is going to be different. This is the chemical synthesis is there. Somebody has done, Dr. Yoneda has done the chemical synthesis of this particular compound. This is the total near about 40 steps is there. And in that one, only 1% yield is there. So it is total synthesis versus the biological chemical synthesis. It is a distinct advantage is there when we are going to use enzyme for the synthesis of a cofactor as compared to laboratory synthesis where we are going to use lot of chemicals, biochemicals, and do some environmental polluted gases, all those things we are going to eat, and it is not going to be very biological environment is there. So for that reason, um, people have started these things. See, this is the, now I am talking about this little bit about tuberculosis. In tuberculosis, this most important enzymes which is involved into that one is these two. This is the another F420 enzyme involved into the application, biocatalytic application, because these are the in different enzymes, enzymatic reaction where F420 is the cofactor involved into that one. This type of reaction is there. So if you want to use this F420 for different type of reactions, you can perform with that one. And these are the different family of enzyme is there. See, this F420, what is doing, it is the in terms of whatever drug we are going to take, in that one, it is protecting that particular drug. It is not to be cured by the chemical compounds. Just like here it is there, this revamping was there. This particular drug, I have taken 4 months, 300 mg per day to cure the latent TB. So this is the, but this year 420, it is protecting the TB, not to be cured. So this is the very small amount this thing is there. So based on that one, whether that thing is going to be there, one can go for these are the primary drugs is there, isoniazide, rifampicin. These are the primary TB drugs are there. And I was taking this particular compound 4 months. And during that time, I got weight loss, little bit appetite also. It was lost. So I thought about the taking of this particular chemistry to understand a little bit. It is not bread and butter. I was looking for that one, but I wanted to learn that one. And thank to Pratibha that she has given me time to explain. And most important, I want to stand my own legs. That is my impression is there. It is not that I want to pose that I have produced 46 students and they are working, or most of them are professor, 10 my students are in US. That kind of things is not there, but I ask them also for help, but due to other reason, they might not be allowing me to even discuss with me properly. Okay, after the retirement, this treatment is there. It is not, I am not blaming them, because they are doing their own work. Why I should go and do that things? This is the second type of tuberculosis drugs are there. Second line of drugs is there. This this cyclic peptide, this is they are trying to give an injection also. On the clinical trial is there, and they are trying to do that one. This is the water soluble is there, so one can make injection from that one for tuberculosis person who are not interested to eat the tablet 300 mg at least 4 months. Um, this is the third line of drug is there. Uh, this is the drug. Why I have chosen this one? I have gone to this particular. See here, why I have taken that F420, because this is the new compound is there. It is approved by the FDA in USA 2019, this particular drug, and they are saying that F420 is involved their mechanistic biological mechanism for that one. See here, it is the enzyme is there DND, and it is going to give that yellow species and this particular compound, and this is the things which is responsible for the killing of the bacteria. In crude term, you can say this particular and these things. I am going to stop. Don't worry. This is the synthesis of that particular compound. Compound is there. Here, pretonide. This is the drug is there. So this is the easiest compound is there. So this we are not going to, are not interested. This is the, see, I want to speak here, environment. I've collected some transparency on environmental, but I'm not going to speak because other people are also hungry, as well as time is not there. So I'm going to stop here. Only things I thank the Department of Chemistry, who are with whom grace I am getting at least pension, so I can eat happily and give this one. I am standing my own leg. I am speaking also, so I am fine. Thank you very much.
So, are these cofactors have any relevance in pertaining to human cells?
Yeah, they are going to.
They are present in human cells?
Yeah.
Are they important for xeroderma pigmentosum?
No, that tumor I don't know, but these cofactors, because one of the important things here is there, this the cofactor are going to solve some of the environmental problems, just like it is responsible for the methane biosynthesis, whatever the methane is there, and methane emission is the one of the problem is there. So in that methane emission and that thing, certainly this cofactor is involved. Methanolysis, all the 8 enzymes are involved, and this one particular F0 and F420 are very important for doing the reduction and oxidation for going from CO2 to methane. So this is 8 cofactors are involved. So certainly they are going to affect if it is there.
They can act as a competitive inhibitor or additive factors in terms of NADPH reactions.
Yeah, it is going to be just like NADPH reaction is there. In that one, it is opposite stereochemistry is there. Hydride transfer, just like in case of NADPH, if it is addition is trans, but with this cofactor, F420, it is going to, addition is going to be cis, and you are going to have different stereochemistry about that one. Thank you very much. At least it is giving me more.
Thanks, Professor Chauhan. Please.
We would
My
like to
purpose is served.
felicitate Professor Chauhan. I request the chairpersons to kindly do the honors. We'd also like to present him the conference kit. And I request Chanchal to kindly present a special painting to Sir. To conclude this session, I would like to thank our esteemed speakers for giving us an insight into the world of anti-malarial drugs like tetraoxane, palladium catalyzed isomerizations, and the chemistry of cofactors like the F0 and F420 in health and environment. We would also like to thank and felicitate our chairpersons for this session. I request Professor Alexander to kindly felicitate Dr. Ranjana ma'am. I request Professor Decker to kindly felicitate Professor Kukreti. Professor Decker to kindly felicitate Professor Kukreti. I would also request Chanchal to kindly present his painting to both our chairpersons. Thank you so much. We now end this session and we can proceed for lunch. I think in the multi-purpose hall.